So what's the general equation that we're going to use?
Work of friction equals changing kinetic energy plus changing.
Sure. What is our change in kinetic energy?
1/2.
Because we have essentially zero velocity as we go over the first hill. We just barely make it over the second hill. So again, negligible velocity. And then for, change in potential, we can just plug in our normal formula. And then plug in numbers and calculate. Remember, delta y is final minus initial, so 39 minus 55. And then we calculate our away. So work done by friction minus 83104. So what is the change in internal energy? And positive 83104 joules. That's actually a concern for roller coaster designers, is the amount of internal energy, commonly called heat, that's generated as they roll along the track. There was actually at Six Flags in Chicago, they've torn it down now, but there was a roller coaster that was closed like 75% of the time because the track kept overheating.
Wait, could you explain why velocity is negative?
Well, I said V naught is 0.
Yeah.
And then they just barely make it over the second hill. So that means as they're going over the second hill, if they just barely make it over, then their velocity is really itty bitty.
Right.
So approximately 0. Alright, spring with constant 55 newtons per meter has one end attached to the floor, block with mass 310 grams is pressed into the other end. Compressing the spring 22 centimeters beyond where it would be in equilibrium, then it's released. By the time the block reaches its maximum height, air resistance has done minus 0.21 joules of work. What is its maximum height? And we do have to say from equilibrium here, because we don't have any other reference point. Also, I feel like this was a little bit ambiguous. What do we need to know about this? What do we need to know about this 22 centimeters? Where's this statement here is ambiguous?
Is it because we don't know which position?
Yeah, it's not really clear which position it's talking about. This equilibrium. Is that equilibrium of the spring or the mass spring system? I mean, it kind of sounds like equilibrium of the mass spring system because it says where it would be in equilibrium, the block. I don't know. But this it isn't necessarily clear. So I'm just going to say that this is, I've arbitrarily decided that this will be the equilibrium of just the spring. Because that makes it harder. Yay! Oh yeah, I also want to note that just like when we were doing problems where mechanical energy was conserved, we can rearrange how we write this. Saying this, if we just rearrange stuff, then this is the same as saying the work done by non-conservative forces is added to the initial mechanical energy to get the final mechanical energy. So whichever way you prefer to think about it, you can think about it. It doesn't matter either way. Okay? Okay. So we have work done by air resistance plus what our initial potential energy, where we have both spring and gravitational. Initially we have 0 kinetic energy. Then in the final thingo, we have only gravitational potential energy. It won't be touching the spring anymore. And at maximum height, our velocity will be 0. So the kinetic energy will be 0. Then we can plug in numbers. Spring is compressed 22 centimeters, 0.22. And that also means that it's moving down 0.2 centimeters, so our y naught we can say is negative 0.22. Or I put the minus out front. And that will get us our height relative to equilibrium. David, what are you doing on your computer? Oh. Okay, there's a calculator on my desk. Alright. 33. Take a minute to read that. Maybe draw a little picture if that helps you. So if I'm drawing a little picture, I guess the problem doesn't explicitly state this, but the spring is horizontal and the mass is on a surface of some kind. So, Andy, which version of the equation do you want to use? Okay. Work non-conservative equals delta K plus delta U. Okay. Work done by non-conservative forces would be what, Andy? Right. The floor is rough, so there is friction. So work done by friction. Change in kinetic energy. What should I put for that? What's the initial speed of the mass? What's the final speed of the mass? Andy? Mm-hmm. So our change in kinetic energy is 0. What is our final potential energy? What's our initial potential energy? Okay. But the question doesn't ask for work done by friction. It asks for the coefficient of friction. Okay. So what can we replace work done by friction with? And what is force of friction? UK times Fn. And in this case, what will Fn be? If we write Newton's second law. We would have that. So just normal in gravity vertically, and the acceleration is 0. And our negatives go bye-bye, which is good because the coefficient of friction is a positive value. And so then the coefficient of kinetic friction is equal to 1/2 kx0 squared divided by mgd. Andy, what should I plug in for all these things? Half is a half. K is 210. X0.
Negative 10.1. No, 0.101.
Okay. G, of course, is 9.8. Yep. Yeah, because friction will be acting the whole time. The friction doesn't start when the spring stops being compressed. Friction's going on the whole time. Yep, and then we can calculate. Easy peasy, right? No problem, no problem. And look at that, that's even a reasonable coefficient of friction. Good job, Mr. P. I'm going to strain my arm here. Questions about that one? You okay with that?